Okay, so I wrapped it with the copper wire. I'll have to continue this with iron wire, and then after the iron wire, I'm going to continue it with aluminum wire. I have all the phase wires hanging out for a linear motor. I have to add the suspension coils alongside to replicate the indentations of the initial gauntlet of the iron suit system. So that will replicate the patch parts, three-dimensional patch parts of the Palmer, alongside from the central core of the repulsor. The linear solenoid, I have to add the aluminum here. I have here steel wire. Iron. I have here for the pancake coil. I'm going to add an additional pancake at the bottom. And I'm going to add an additional pancake right here on the top. It's going to be a little bit, I think I'm going to make the shield pancake for the motor, the gauntlet shield pancake. And as at the bottom, I'm going to make pancake telescopic donut coil here. And I'm also adding the aluminum wire to it, along with the iron wire to the gauntlet. And then I would start on the electrochemical electromagnetic battery, which is going to be right there for a Hall effect, to phase this voltage transformer, step-up voltage transformer, to repulsive force in here. My name is Jermaine Morton, and goodbye. So, I added the cage. This is about an inch thick, about an inch and a half, so it's about almost an inch and a half thick as far as depth. And the diameter should be able to fit the electrochemical. So I'm using electrochemical Hall effect, using dielectric mesh powder and ferromagnetic powder, and I'm going to roll it around like an accelerator and use a Hall effect sensor so I can be able to transmit the energy to induce the currents here and through the iron wire towards the copper, and the copper back towards the iron wire. I am going to, at the other segment, I put a non-coated copper, and then I put coated copper. I want this to be a collapsal. I put the iron wire so I could use the copper dielectric to flux the iron wire to increase the frequency, the wavelength, and I'm going to put the aluminum on this side, so it's going to be straight across towards the face and the palmer and the fingers, frontal of the finger back. We divide the portion with the two sheets, metal sheets, and I use copper on this side. So the copper is going to be fixed on this side, so I'm going to close it with copper because the suspension will make the copper in the gauntlet move horizontally, vertically in the air, horizontally like this. So it'll float up in the air like this because the aluminum is on the bottom of the exterior, and the coil, because of its inertia, because of its radiation, because of its force, because of its energy at which it transmits, is a repulsive energy, along with the aluminum sheet that's going to be underneath the bottom of the gauntlet, and that's going to push the gauntlet vertically into the air like that, up and down, so up and not down. Now the copper sheet on the back will cause it to repel because it's in a vector of the aluminum sheet that is creating a field. The aluminum sheet is going to be phased with a DC charge as far as the aluminum front sheet, along with the copper receiving a DC charge with the coil-induced currents. Now, the turns of this exceed 68 Teslas. So I don't want to tell you how great the gust is, but it surely exceeds 68 Teslas. So it's way more Tesla gust than that. And the pound force of it, like I said, the pound force is way greater than what you think. So the aluminum sheet that's going to be mechanically fixed to the surfaces within vector of the magnetic field is going to try to escape, but because of the aluminum sheet being so lighter than the mass of the coil turns, it's going to be yanked along with it, as long as it's within the magnetic field, stuck mechanically and constantly flowing the air in a horizontal position in linear motion when the two different are phased with a charge. Now the pancake coils is first the donuts series telescopically within one another inside its air gap, may not give energy to the linear coil that is moving up in like a solenoid in a helix shape. So it's not going to induce currents here. So these two will not share each other's currents. However, I still will have to phase in the Lenz's law force upward for the counterclockwise in order to move the sheet away, of the aluminum to move upward in the opposite direction. But if I phase it clockwise, it will allow the sheet to move downward. Because it's mechanically connected to it, it also may move downward along with the sheet. However, because of the repulsive force common to one another, this involves it to force its way back up into the air. So it's going to be hard to bring it down with sending voltage to it in order to bring it down to change the Lenz's law phase point in as of the right-hand rule. So that's not going to work typically with this. So I have to turn down the voltage to the system. Now the windings to increase a flux to the coil windings, and to increase a flux to cause this transformer to transmit the energy from these coils up here up top to down here, and this back to up top to share the current in the cycling. So I'm going to be able to use a motor to power the internal parts, and it should be a submersible to move the materials, the elements within electrolyte liquid. Source of It's not finished. I still would have to coat this with rubber. I still would have to, before I coat it with rubber, I still would have to place the aluminum, then I got to coat it with rubber, then I could come back to place with another housing as far as titanium if I wanted to make the exterior looks nice. However, it resembles in those same likenesses of the iron gauntlet. However, these coils are padded down by rubber, and I have a rubber hammer, so I may shape it to smooth it and to blend it in, so it won't be so donutly bulked out. So, and shape it with the hammer after I use the glue, quick drying glue, to hold a positional area so I could be able to mat it in like clay and get it to shape its form as far as my hand shape. So it's way bigger than my hand. Just because my hand is frontal doesn't mean that it's actually, my hand is bigger than it. No, it's actually bigger than my hand. So in the depth, the size of this wideness is like, shit, this is about more than 4 inches or 3 inches wide. As for comparison of this box right here, I can take this box and put it right here, and this box is very wide. So for the side of my hand being like very thin, I don't think that, you know, I have a lot of room inside the cockpit. This is only spun on the outside, but it's just some other rubber. With this, and take this with rubber, with thermal resistant rubber, so the outside doesn't have wild heat and stuff like that. So, I am going to use a mini-fold phase for the phase wires, mini-fold, so I can connect it, and I can modulate the mini-fold with any kind of input to increase the voltage or to change the voltage to change the electromotive of the system's first velocity of the electrons or the charges, the static charges of the hertz. What I want to do is make sure that I minimize the wavelength of the electrons and set it at high velocity in hertz, in series in hertz, because it takes momentum in order to get a conductor to get real hot. It's like putting my hand through a lighter. This cannot burn if I'm moving it back and forth, oscillating it so fast that it cannot set on fire and cannot increase in heat. So because I'm constantly moving it, it really just doesn't get hot enough as far as over the thermal rate. So the same thing when sending in inductors, same thing like using toilet paper or tissue and just running through. Eventually, we know that tissue is supposed to burn, but when moving it with a torch, the torch is on, as you can see the flame. So when moving it with a torch, you really don't catch fire when you're constantly. So it doesn't really, that's what momentum, like I said, it would take momentum. Now, like I said, to try it again, and to go over it with, you know, over and over real fast. So when I'm using a voltage to it, doesn't really cause it to exceed overheat. So when I'm using harmonics to induce currents in it, it doesn't really generate that much heat at all. So you don't have to worry about, I don't have to worry about burning my coils. I'm going over 200 hertz per 200,000 hertz per nanosecond. So that's it. That was the mystery to figure out. That was the breakthrough, you know, to keep myself from burning out the coils and overheating where everybody's complaints was about. So I fixed that. My name is Jermaine Morton, and goodbye. Wish me good luck, and I'm going to continue and help you right back.